Hey, I'm Dan Kuba. I'm a Senior Solutions Architect here at Atym, and we'd like to introduce you to some of the technology that we're building. So we have a tiny embedded containerization solution based on WebAssembly targeted at low-resource embedded devices. And that could look like anything from low-resource Linux devices, so somewhere in the range of under 2 gigabytes of memory, all the way down to RTOS-based devices. We specifically support Zephyr today. However, we're OS agnostic, and we can run on any particular RTOS.
It says kilobytes.
Yes. So what that's all about is the overhead for our individual containers is very, very, very tiny. So as opposed to a Docker image, which could be hundreds of megabytes to many, many gigabytes, we have a very tiny overhead for our containers. And that can be as little as 300 bytes that we're adding on top of a simple application that we've got.
How can it work with so little data?
Well, a lot of the intelligence is built into the runtime. So when you build a Docker container, a lot of all the dependencies are all built into that Docker container, and it's actually running its own Linux distribution inside of there. With our technology, we've put a lot of that into the runtime itself, which offers that API abstraction layer. So when you write an application, only your application is the part that's containerized. The runtime sits on all the different devices, and it's built for the different architectures that we have and also the different operating systems we have. But a lot of that, the heaviness sits there. And even that is lightweight as well. On Linux, we're talking about 4 megabytes. And on Zephyr, we can run on devices with as little as 128K.
And you can get all the containerization and all, you call it like the security or the design. It's doing what people want to do with it?
Yeah, so one of the really awesome things about WebAssembly is that it's a virtual CPU architecture. So essentially it's a compiler target. And what that means is you can compile any language to it, and when you run that code, it's actually sitting inside of a memory space that is segmented off from the actual host itself. So what that means is that you don't end up being able to access memory that the host provides for things like a network interface or direct access to GPIO or memory that's shared with other processes, even other containers. It's all sitting inside this specific space.
It's impossible to get out of it.
It's a software boundary. So even if your device doesn't have an MMU, we act as basically a soft MMU.
And for sure, there's no way to get around?
Well, I mean, the software won't let you do it. So if I try to make a call outside of that memory space, the container is going to crash.
All right, what do we see on the screen here?
Yeah, so this is an example of a containerized application that we've got. This is running on a NXP i.MX8 board that's running Linux. And what we've done is we've taken LVGL as well as socketCAN, and we've put them together to create sort of a virtual dashboard that you might see in a car. So this board is actually simulating an ECU on the Linux side, and we're piping that CAN data out of one CAN interface into another. And then inside of our container, we're running all the native POSIX APIs, and so we're able to access that CAN bus information over socketCAN. When we read all that data in, we translate that into the objects that LVGL needs to drive itself. And then we have an API that pushes out into a frame buffer that's actually inside of the memory space of the container. So no copying across the boundary. We write frames out to that using LVGL. And then on this Linux runtime, we're using SDL to display those frames in the little window you see there. Now, if only my board was working, I broke it, because that's how demos go. We have a NXP RT1064 board running Zephyr that this exact same container binary can run on and do exactly the same thing. So our abstraction layer takes care of all the stuff around CAN and also the display interface, and so it's able to use the same exact code that we wrote to do the demo on both platforms.
So you talk about NXP and this one?
Yeah, this is also an NXP board. They just happen to have a convenient set of Linux and Zephyr-based.
So it's i.MX8 M+.
Yeah.
And what's the advantage of your technology? What is people really going to be able to do this?
So there's a number of things. One is the security benefits I was talking about, being able to segment off applications from either the host or from other applications. You can imagine a web server that becomes compromised and it's deployed to a device. Well, now the impact of that is probably limited because now the other applications that are running on that device may not be affected by that because we've segmented off the memory of that container. So the blast radius is contained. Additionally, because our containers are really tiny and a lot of the intelligence sits in the runtime itself, you can imagine that maybe you have an actually fairly powerful device sitting out there, but it's on a satellite connection. this container is 750 kilobytes. It's very, very tiny. Now, of course, this is fairly simple, so a more complicated app is going to look bigger than that, but you can now deploy fairly complex applications over a thin pipe, whereas with Docker, you'd have to deploy the entire operating system and all the dependencies associated with that. We don't have that same challenge.
And is this something that's very much in demand? Right here, I see this Edge AI Foundation.
Yeah.
So does it enable Edge AI stuff?
Yeah, so one of the really cool applications of this as well, AI developers are very familiar with cloud native development. And one of the things, because these are containers and they are treated like containers, in fact, these containers can live in the same repositories as Docker containers alongside existing CI/CD workflows or whatever deployment pipeline that you have. This allows developers to have a much closer experience to the cloud native experience they're pretty much used to today, but on devices that they would otherwise find inaccessible. There's a lot of folks out there that don't know C or C++, and they work in higher level languages, or they don't really understand hardware at a deep level. And this technology allows them to work in a workspace that they're very familiar with, a tool chain that they're familiar with, and a deployment strategy that they're familiar with, instead of having to go and become an embedded developer or work with an embedded developer who may or may not be on staff.
Can you deploy kind of like new models or something inside your containers, or does it help
this
in security or something?
This is a deployment strategy for that sort of thing. So you can imagine, continuous integration of AI models. I want to collect data from the edge, I want to improve that model, and I want to deliver that model back down to the device. Having a system like this that allows you to containerize that app and deliver that app and manage that app at the edge is something that we haven't really seen on embedded devices. Of course, you can do that with a complete firmware update, but that assumes that really the only thing in that end firmware image is the AI application, or you're going to retest every time you have a new AI model, all the other features and functions that sit there. This makes it much smaller in terms of dependencies, so you can just update one piece of your application, maybe your AI model, maybe it's a web server, maybe it's something else, without having to worry about the rest of the system. And
with the regulation in the EU, in Europe, are you enabling stuff that makes secure updates easier, faster,
absolutely,
more secure? Is
absolutely
it part of that?
Yeah, and that's a big driver for this. Customers of ours are asking, how do we comply with these new regulations? And the answer, being able to segment off applications from other parts of the host, being able to understand what is actually running at the edge with an SBOM, we feed into all of these tools and all of these different opportunities there with the new regulations that are coming out, and people are really excited about that.
And what's the business model?
Yeah, so one of the really cool things about this is the core model that actually provides the runtime in which WASM modules will run at the edge is open source. It's called Ochre, and it's open source to the Linux Foundation. We believe in sort of a vendor-neutral approach to something like this, and we're driving for this to become a standard within the industry since we're the first player in the space in this regard. Now, Atym, we provide the orchestration layer that sits on top of that. Once you have a container running at the edge, well, you need to be able to manage that. You need to be able to manage the life cycle of that. Maybe you need to manage that across 1,000 different devices. And so we have a cloud platform that allows you to do that. And another really cool thing about that, WebAssembly, you can actually compile it to a native binary to get near native performance out of a particular application. And our cloud will automatically compile your developed applications for the target architecture that sits at the edge, allowing you to get the best performance in a mixed fleet or for the particular device that you're deploying to.
Cool. So are you a small company, or are you a big company? Or
We're small. We're 10 folks right now, a mix of full-time and contractors. We've been around for a couple of years.
In Austin?
Our CEO is headquartered out of Austin, but we're a global team. I'm out of the Bay Area. Brian, our head of sales, is out of the Boston area. Our CTO is in France, and we have a developer team throughout Europe.
And you're doing the connections with all the people in the embedded world?
Yeah, we're really excited to be here. It's been great to meet with a lot of partners and folks who are inspired by this technology. Some of them have heard of the various pieces of things that we built. Some of them have no idea that this was even possible on microcontrollers. So it's really great to be able to connect with people, talk to them about what is really possible, and get people excited about the future of embedded development.
And I just see my friend is here.
Hi, how's it going? Charbax.
So you're hanging out with all the cool guys here at the Embedded World?
Absolutely, yeah. That's it's been the hottest booth at the show.
This has literally been the place I've been hanging out. This has been where I've been hanging out, the Atym booth. Yeah.
All right, cool.
HDMI technology powers the global ecosystem of connected devices, enabling advanced displays that deliver immersive visuals and sound across entertainment, professional, and everyday applications.
As the preferred technology for digital AV connectivity, HDMI technology and the features and benefits it enables
links billions of products worldwide, from HD TVs, set-top boxes, and laptops to gaming consoles, projectors, and audio-video receivers. It provides the reliable, high-bandwidth connectivity needed for today's ultra-high-definition video, lifelike color accuracy, and immersive sound formats. HDMI technology drives innovation across industries, including digital signage, medical imaging, education, and esports. With unmatched performance, interoperability, and scalability, HDMI technology continues to define how content is created, shared, and enjoyed around the world.